Did you all bring your own whiteboard markers? So I guess the whiteboards are not useful to anybody in the classroom then. Just a little professor humor as we get started. I'm going to ask you to sit at tables with 4 to 5 people each. So minimum 4, maximum 5, unless that's got to work, right? Mathematically, it's impossible that doesn't work. Maybe it's got to work. It's not especially that important either, but I don't know. I think it sets a good tone that you follow my instructions at the beginning of the term, right? And I'll try to start right on time every day. There was some question, several of you emailed me because Workday had us at 2 locations at the same time on Tuesdays and Thursdays. Yeah. Olin 107 is the correct location. We will only be here on Wednesdays. And I've got to say that this is my least favorite classroom in the world. In fact, I think it is the poorliest designed classroom in the world. So sit at tables with 4 to 5 people. If you're just coming in, find a group where you can be at a table with 4 to 5 people. The reason is when it's open. So I think it's probably okay when the 2 rooms are divided. But when it's opened up like this, I want to stand in the middle so everybody can see me. There is no whiteboard that I could use, and the room doesn't come with a document camera, so I have to make my own. And also like the echo capture camera things that WPI uses, they record video at like the poorest quality possible. And I'm kind of vain. So when I go back and look at the video of me, I want to be able to see me. And so that's why I do this. I have not yet published the syllabus. You've probably noticed that. I will do that later today, and we'll actually talk about the syllabus tomorrow. What I want to do today is actually just jump right into some learning. So we will start at 11. This is pretty close to 11, so let's go. I made myself a little schedule so I can try to stay on track. Focus. I got to figure out how to disable the autofocus on my document camera there. So sit at a table with 4 to 5 people, or split your personality. That's kind of optional. It's up to you. But anyway, so this is ME 1800, right? That's what everybody came for. I call the class Introduction to Manufacturing or Introduction to Manufacturing Engineering. I think there's this long title that's in the course catalog. It is a title that was clearly written by a committee, but this is Introduction to Manufacturing Engineering, and starting right on time. It's perfect. So we'll talk a lot about what it means to do manufacturing engineering and manufacturing, but a lot of the time in this class, we're going to talk about CNC machining. And we're actually going to talk a lot of time in this class about CNC machining and using it to make prototypes. There's a few reasons for that. One of those reasons, well, I guess this is the middle of the year. Is this anybody's first ever class at WPI? Could be if somebody transferred it in, right? So we've all had classes at WPI before, right? Have most of your faculty members been tenured faculty or tenure track faculty probably? No? Most of the faculty at WPI are. And I had one of them tell me once, he said, instead of giving it away, it's one of the male professors here on campus, still works here. He said, well, they can make me teach it, but they can't make me teach it well. And the reason for this is when we hire faculty at universities, we tend to like to hire faculty that do research, that bring in research funding, make the university look great. I actually wasn't hired that way, so no worries about that for me. But I do have the other problem. But anyway, these people, they do research in a specific area. Right? When you do PhD level research and stuff, it's very focused in a specific area. But when you hire them, you also tell them to teach classes, because that's how we get most of our revenue here at WPI is you guys. And anyway, no matter what the class is, no matter what the syllabus, or I guess the syllabus they control, but no matter what the course description says, they just tend to teach the thing that they know the best. This is convenient for us because actually the thing that I know the best is CNC machining. And that wasn't the case when I started this, but actually since I got hired to teach and not to do research, I figured I'd learn about the thing that they hired me to teach. I took M1800 in 1994. What is that, 28, 29 years ago? Something like that. It was slightly different then. So I'm a WPI alum, right? Because you don't have to have graduated to be an alum. Did you know that? You just have to have paid them money and started. Then you're an alum. They will claim you. They claim all kinds of people who didn't finish but started. All colleges do that, right? Harvard claims Bill Gates. So anyways, is it Harvard? Is that the Bill Gates one? I think so. Anyway, it doesn't matter. So I took M1800 in 1994. I got a C. I'm pretty sure the C was a gift from the professor. And by gift, I mean he did not want to see me again. So he passed me, right? Because C's get degrees at WPI. When I started the class, and part of the reason I got the C was because I became disengaged with the class. Have you ever had a class where you became disengaged? Yeah, we all have, right? So I became disengaged with the class because when I started the class, I was going to become a machinist. And I was going to learn how to use those machines. And I was going to make so much cool stuff in that machine shop. And like the world was going to change because I was in that class and I was learning that stuff. And as I got in the class and went to the labs and met the people that ran the labs, it became abundantly clear that there was, in 7 weeks, there was no way they were going to teach me enough that I was actually going to become a machinist. It didn't really feel like they welcomed people coming back and doing stuff in the labs after they finished the class. I mean, there was a few kids, and they had gotten a job as a work study there as a freshman, and they'd spent 2 years sweeping the floor. And finally, the machinist had enough confidence that they'd teach him how to do something. One of those guys that worked here at that time, I actually overlapped with him when I was in graduate school. And I remember Joe said, if you can't teach it to him, because if you teach it to them, they're going to want to do it. Anyway, fast forward 2006, I got hired to teach this class and to run the manufacturing labs. And I still had that bad memory of realizing that I didn't get what I wanted out of it. And so my goal when I took over 2006 was to at least take away the stigma of people don't want to be here, and to change it so that people feel welcomed and people feel enabled to do stuff. So I said we're going to talk about manufacturing, CNC machining, and prototype manufacturing in the class. We're talking about CNC machining because that's the thing I know the best. I've taught about 10,000 people how to do CNC machining in the last 17 years or so. I've had 450 of them that were long-term displaced workers, and they didn't count as successful until they'd held a job for 6 months. And so we did that. So it's pretty cool. So I know something about CNC machining. That's why we're going to teach it. And that's what the course description says. So it's kind of cool overlap. You don't always get that here. So what are we talking about today? Today I want to talk about how we go from that concept in our head to the finished thing that we wanted, right? So I call it the process of going from art to part. So we're actually skipping a little step, right? Before we could actually have, what do you think the art is in this case? So we're talking about making prototypes. What's the art in going from art to part? Yeah, go ahead.
Some kind of sketch or design.
So some kind of sketch or design. What's your name?
Bryce.
Bryce. I won't remember later, but I'm going to try. I'm going to make a valiant effort. I promise. It might work if you always sit in the same spot, but since we're in two different classrooms, that's going to be kind of tough. So Bryce says the art is some kind of sketch or design. Absolutely. And it can be a napkin with a sketch on it. I used to own a company. We had a service we called Napkin Part. So if you sent us your bar napkin with a sketch on it, we would send you back the part. That was more expensive than the traditional way because we had to do a lot more engineering when it was napkin apart. But yeah, so the art here is the sketch. But before we can have that sketch, what do we need? Somebody over here. Back corner table. Blue clothing. What is that, a sweatshirt? It's a hoodie? Yeah, okay. Blue hoodie. What's your name? Simon. So Simon says before we can, see how I did that? It's not the first time you got that, is it? So Simon, tell us, what do we need before we can have the design and the sketch? We need an idea, right? So it actually comes from that idea, that thought that's in our head. We got to have that. Once we have an idea or a thought, then we can do the sketch part. Who took this class because they thought it was about the design part? Anybody? Perfect. So we'll talk about design. We'll talk about good design practices in the class. But this class assumes that you have the design, that either you or somebody has created the design. So we're starting with the art here. And so if I want to go from my idea, I got to get my art. There's a lot of work, a lot of engineering that goes into that step from idea to art, correct? Yeah. Okay, just so we're not saying that part's important, it's just not what we're going to talk about in this class. So if I've got my idea and I've encapsulated my idea in a sketch or a design or a drawing or a solid model or whatever I've used to capture it, what I really want is my part. So what do you think the next thing is that we need after we've got our design? Yeah, go ahead.
It depends on if you've
Other blue hoodie.
It depends on if you've done like a basic sketch and you haven't added dimensions.
Let's just assume the art is sufficient to make the part.
You're gonna want to know what material you use.
All right, so we're going to want to know what material. So there's some things we need to know. So we need to know what material. Is there anybody that's really good at spelling? You're really good at spelling? So you do the red squigglies later. Because I am not really good at spelling. And if I need the red thing back, send it back to me. We need to know the material. Is that the next thing we need? Well, actually, as the manufacturer, as the manufacturing engineer, how do we know the material? We know the material because the designer, Bryce, the designer, he told us what material to use in his design specification. So we need to know that, but it's part of the design. Yeah. Yeah, so the design has to specify the material. It has to specify the dimensions. It has to specify everything that would quantify that part well enough so that we could look at the part and look at the design and do some quality inspection and decide, does the part match the design? So it needs to have all that information. But once we have all of that information as the manufacturing engineers, what do we need? Is everybody wearing a hoodie today except me?
You need to be able to go from the part to instructions on how to.
Right, so we're going to need some instructions. What I always say is after we have the part, so these are things we need to know. We'll put that over there. But after we have the part or the art, the next thing we need is a plan. Does that make sense? We have to decide how we're going to make the part. So one of the ways that we could make the part is CNC machining. And since that's the thing I know about, that's the thing this class focuses on. And so we're going to have to know the plan. Now, who could describe in a sentence what CNC machining is? Over here. giving instructions to a machine that could manufacture something. I would say that is a very high level, accurate description, but it contained no information. Bryce.
It's like taking a block of something and then machining it down into the specific part.
All right, I kind of like Bryce's idea here. It's taking a block of something and machining it down to a specific shape or part, right? It's blades, right? And so that's subtractive manufacturing. Now, CNC actually stands for computer numeric control. Don't ask, well, you could ask me why. So it started before that. Before we had CNC, we had NC, numeric control. And in numeric controls, we did some programming, and then we used some information to tell the machine, and it was like punch cards, and the machine tool actually had a little computer in it, and it just didn't have the kind of computer interface we're used to. When people started putting computer interfaces that interacted with people on the machines, well, we already had NC machines, so those are the ones with the punch cards and the tapes and stuff that ran through. We had to call it something else. So we call it computer numeric controls, because we're still selling to the same people. They know they need the NC machine. So we have the little C in front. It's all a marketing thing. That's why CNC should be just CC, right? Computer controlled machining. But CNC sounds more sexy, so I guess we go with that because the marketing people decided. Anyway, so the machining process itself, and we're going to get into the physics of the machining process in depth in this class. The machining process itself is a subtractive process. It's like carving a statue. If you've ever used like a pocket knife and whittled something, if you have, it probably looks better than anything I ever tried to whittle. But if you've ever done that, there's a thing where like the art student asks the art teacher, how do you carve this piece of ivory into an elephant? And the art teacher says, you take away everything that's not elephant, right? And so that's what CNC machining does. It's you take your material that's been specified by the designer, and you take away everything that's not the part the designer wants. All right, so we need a plan. We need to decide how to do it. There's really two major kinds of CNC machining that we're going to focus on here in the class. It's called turning and milling. In turning, the workpiece rotates, and there's a tool that goes in and out. And if you've ever used any of those like CAD software, SolidWorks, or any of those things, it's sort of like anything you can make with a revolve operation, you could make in a turning operation. Call it turning, we do it in a lathe. Some people call it lathing, they're wrong. We call it turning, we do it in a lathe. I get to decide because I grade the tests. Milling, on the other hand, we do in a milling machine. Sometimes we do it in a VMC, which is a vertical machining center, but same thing. In milling, so you got an idea of turning or lathing, right? You get the workpiece spins around really fast. The tool goes across it and goes in and out, and it can make a shape like a candlestick or a chess piece, except for like the rook, or not the rook or the knight, or pretty much any of the ones that have non-symmetrical features. Milling, the tool spins, and it moves in X, Y, and Z through the workpiece to carve away. So we typically use a Cartesian system when we talk about milling or turning. In both cases, the Z-axis lines up with the spindle. So the spindle always rotates about the Z-axis. So if you think of a lathe, when you get to the lab, you're going to see all these. Think of a lathe, the X, Y, Z, and it's always a right-handed. Well, the ones we have are always a right-handed coordinate system. So you do the X, Y, Z thing, right, with your hand. And so Z, that's Y, this is X. Same thing. So in the lathe, you just lay it over, and it's still lined up that way. That'll make it easier. All right, so in order to do either of those processes, we've got to move the tool through the workpiece material. And we got to spin the spindle while we're moving the tool through the workpiece material. So what do you think? If I had, say, aluminum or stainless steel, which one's going to be harder to cut? You say stainless steel is going to be harder to cut. Anybody disagree? Think aluminum is going to be harder to cut? You think aluminum is going to be harder to cut? Aluminum is gummy. That is true. Copper is even worse than aluminum in that sense. In reality, I wouldn't say that either one of them is harder to cut, but the stainless steel will totally take more energy, right? So it takes a certain amount of energy to get, so what actually happens, and we're going to get into this in the class, what actually happens is you've got say it's the stainless steel, right? You've got a grain of stainless steel. This is if you're zoomed in with like the electron microscope. You got another grain of stainless steel here. You got a bunch more of them, and they're all mushed together, and they bond together, and they form that lump of material. And so as we do our cutting, we're pushing on it. And as we push on it, it shears along those grain boundaries. And as it shears along those grain boundaries, it takes some certain amount of energy to make it shear. And so stainless steel takes way more energy than aluminum does. And there's tables and stuff. We'll get into that later in the class. But so we've got to have our plan. Our plan has got to include some understanding of how much energy it's going to take to separate the grain boundaries. Because what is energy anyway? Yeah. It's the ability to do work. All right. So what time is it? 18. I got to check my schedule. Sometimes I get carried away. All right, we're still sort of on track. Only 10 minutes behind. I'll talk faster. He says the ability to do work, right? So energy is the ability to do work. What are the units that we use? If we get it back to like joules. So how do we get to the units there? So what's work? Work is a force over distance, right? So energy is the ability to do work. Work's a force over a distance. We all know that, right? We all had physics 1. Okay. I can't resist. I was in somebody else's class. I was going to give a guest lecture, but the other faculty member was getting ready to introduce me, and he's taking some questions from the class. There's a student up in the back, and he may or may not have been he was a student up in the back. He was probably wearing a hoodie. And he asked the professor a question. And I don't remember what the question was, but I heard the question. I'm like, really? But it wasn't my class. I didn't say anything. The professor looked at him, said, "Did you take physics 1? Because, yeah, I took physics 1. You should ask for your money back." I will try to only think it and not say it out loud, okay? So please ask your questions. Anyway, so work is force over distance, right? And so the distance we have to go and the force we have to apply is part of this. How much energy does it take to do the cutting? So it takes more energy, it takes more force. Does that make sense? What happens when you have too much force? Tool breaks. Too much force, tool breaks. Sometimes too much force, tool plenty strong, right? Much force, strong tool, the spindle stops. Right? Who's ever used a servo motor? Who's ever tried to apply too much torque to a servo motor? It goes. Well, the spindles that we're going to be using in class, they're kind of high pitched. I actually have hearing loss, notch hearing loss, right at the frequency of these machines. But it's sort of like, so spindle spinning. Too much force, too much cutting force, strong tool. You can get that with a big diameter tool, could be strong. So anyway, so if we think of the physics of the operation, I said we're going to get back to this path from art to part. So we're going to have our plan. So if we think of the physics of the operation, besides stall the spindle, break the tool, what else could happen? Yes. Yeah, throw the part across the machine tool. When you go in there, either the first or the second mini mill you'll see in the lab as you're walking in the first day, just look to your right at the machine tools as you go by. The first one that you're going to get to is, it doesn't have a case around it, it's unguarded. The next one or the one after, if you look at the wall of the machine, you ever watch like the Roadrunner? Like when it runs into the wall, it makes the Roadrunner impression in the wall. Yeah, well, you can see that on the side of one of our machine tools. I'll show you a video when we do the lecture about that, which will scare the shit out of you when you see the video, and it should. But not of that particular crash, of a much worse one. Anyway, so if you think of the physics of these two operations as we've described them, what are the things that we get to control that might impact how much cutting force there is? Yeah. So we can control how fast the spindle spins, right? We can control that. What else? How much material you're taking at each given moment, right? And so we call that the volumetric chip removal rate is sort of how we talk about it. And so how much material are we taking away? And so how much energy it takes to do this is going to depend on how much material we're taking away at each moment. It's going to depend on what the material it is. It's also going to depend on like how sharp the tool is and what the friction coefficient between the tool and the material is and stuff like that. But in the big factors are how much material are we taking at each instant and what the material is. Those are the big factors. We, as the manufacturing engineer, don't get to choose what the material is. The designer chose it. Damn Bryce and his stainless steel. But we do get to choose how much material we take away. So I'd like to say the four most important process variables in CNC machining are feed speed and depth of cut. It's 4 because in milling, depth has 2 directions. It has a width and a height, right? So and so we get to pick those things. The way we pick them is by selecting a tool path. So we've got a plan. We've got some big general idea. Before we can select the tool path, we have to select the tools that we're going to use. So we've got our plan. Our plan includes the tools, the tool path. We've got to choose the fixturing. And so this is still at a high level. This is in our plan. We're going to pick our tools, pick our tool path, choose our fixturing, right? Because if we don't hold the part strong enough, it's going to fly away. And it is much harder to machine a part that's moving, especially when it's accelerating. All right, so tools, tool path, fixturing. Now, the easy way, and the reason we use computers is because they do, so all this stuff involves math. You believe that? It sucks, but it all involves math. I asked my class yesterday, what's the one thing you don't want this class to be about? 2 people said math. And I will point out that engineering's math. Just a bunch of word problems. Cancel the units. Which is a segue into my next topic. That was a haiku. Right? Who's seen a haiku before? Who's written a haiku before? Everybody? In your English class, your ELA class? So if you're at a table that does not have 4 to 5 people, you should move to a table that has 4 people at it. So we can make tables with 4 to 5 people or get some tables with 5 people to join you. Art, toolpath, tools, fixturing. All right. So we use CAM software. We use CAM software to take the tools we decided to use and help us do the math part of figuring out where to put the tools so that we don't have, it's a bunch of trigonometry and geometry stuff, right? It's all math that we could do, but we don't want to. So we use this software to do that. And it's actually kind of cool because if Bryce did a good job and he gives us our design in a good format, we can actually just put it in the software and then have the software kind of use, I'm not going to say it's AI. I think we need to get some I before we worry about the A part of AI. We need to get some intelligence here. But you can use the tools in there and some recipes and some cookbook kind of things where you can then get it to program a toolpath. Once we've got that toolpath, we actually have to apply the fixturing. We have to put it in the machine tool and have it held in the machine tool. Then we have to, well, we're going to actually have to tell the machine tool where the part is. We're going to have to tell the machine tool what program to use. We're going to have to tell the machine tool where the tools are in its thing, because you can put them in random locations in there. So there's some setup things there. We have to set up the machine. Then we have to run the first article, make the part. By the way, this first one, we should be careful so that if we screwed up, it doesn't explode. So we should be careful. All right, on the first one, but we set it up, make the part. Are we done yet? I said we're going to go from art to part. So we got to make a plan, do the programming, do the fixturing, do the setup, run the program, make the part. Are we done yet? What? We have to inspect. Now, we talk about large volume manufacturing. We're not going to inspect every part, but when we're doing this first article and we're making our prototype, we're going to have to inspect every part to make sure that it is actually the thing the designer asked for. And then one more important step. So there may be secondary processes. Yeah, there may be some secondary processes where we clean up the edges and deburr and paint it and all kinds of stuff like that. But clean up your mess. Come on. We have 1,600 different people that are going to use the machine shop this year. Different people. About 120 people come in a day and do something. So clean up your mess. All right, we've got almost back on time. I have 2 minutes to do something I said I was going to do in 10 minutes. So I'm going to talk really fast. Then we'll be right back on schedule. All right, so who's ever studied like Zen philosophy or Buddhism or anything like that? You've studied a little bit, read about it. Who understands? Who like, does anybody meditate on a regular basis? Should be proud. Anybody do yoga? Anything like that? No, you guys are young. Once you get to be my age, you're into all that kind of stuff because you're trying to figure out how to not die next week. I mean, that's how we leave, right? We die, right? We're trying to figure out how to not die. People tell us, oh, you got to get your mind right. So we go study yoga and Zen philosophy and stuff like that. Okay, so anyway, the other thing is while you're trying to figure out how to not die, so this is a life lesson for the future. While you're trying to figure out how to not die, you also realize there is a lot of stuff you still want to do. Anybody, you probably haven't experienced that because you got the whole world in front of you right now. When you get to be my age, you're going to be thinking about all the stuff that you know you're not going to have time to do, especially if you're going to die next week. So you gotta figure out how to be more efficient at doing stuff. So I went through a phase about, 8-10 years ago, where I was deep in the learn how to get stuff done. In fact, I studied this process called GDT, get things done, or get GDT, GTD, I don't know. I forget what it was called. Dave Allen wrote the book. It was a pretty good book. It talked about how to goal set and get tasks lists and how to not get overwhelmed by your tasks and all that stuff, right? Yeah, that's pretty overwhelming though. And I was also into the like Zen stuff and meditating. I actually, I read Zen for Dummies. There's a book. It was The Idiot's Guide to Zen. I think that's what it's called. I read that on an airplane on my way to Kauai. Spent the next 2 weeks on the beach at sunrise every day learning to meditate. When you learn that way, it's nice. So I was too stressed out by this method. And this guy, Leo Babauta, he had this book called Zen Habits. Well, that sounds pretty cool. Sounds like it's less work than this Dave Allen guy and his getting things done. So one of the things, I won't go into the habit setting thing and all that in the book. One of the things he talked about in there was haikus. And so a haiku is 17 syllables. It's 5 syllables, 7 syllables, 5 syllables. You could all write a haiku right now, right? If I gave you 2 minutes, you could have a haiku. You've all done it before. It's not quite as much fun as a limerick, but it is poetry. So he said, though, that if you want to write the best haiku on a topic, that you have to find the most important 17 words that describe that topic. Does that make sense? So this was my big takeaway from that book. It wasn't the habit system or anything like that. It was this idea of there could be a best haiku. And so I started using this as a tool to focus my mind. And so at the beginning of the day, or especially when I know I got a lot of stuff to have in, what I would do is I would try to formulate the best haiku that would describe that day before the day happened. So you guys are all at tables with 4 to 5 people? All except for 2 of you are at tables with 4 to 5 people? Okay, perfect. Each table, create a haiku in the next, before 40. So in the next 7 minutes, each table, create a haiku that synthesizes today's topic. This process of going from art to part. Now, I did this at a high level, right? We're going to get into detail on all these steps as we go through the class. But each table, working together, come up with a haiku. So 5 syllables, 7 syllables, 5 syllables. Hey,
A haiku about what?
today's lecture.
Okay, perfect.
Today's topic.
We'll see. Okay.
I'll give you an example of one that I did a couple years ago. I'll just write it up here. You can look at it later.
Good job. There you go. Honestly, I'm having trouble fitting it into 7, but extending it to 7.
So you can use poetic license, and it doesn't have to be grammatically correct. It does have to get the point across, right?
Yeah.
I mean, actually, a haiku is supposed to be written in Japanese, and it's supposed to be about nature. So we're already taking a lot of poetic license. Do that on highlight.
Yeah, I know.
How'd you end up being in a group of 3?
Yeah.
What do you got? You got one?
Well, it's still trying to figure it out. So we start with the art, we make a plan, and then we clean up the mess. It's actually. Yeah. Well, seven. We can change everything better. Yeah. Yeah, I don't think it's bad. Yeah.
We got about 2 more minutes. You're done? You're done? You're done? No, I'm going to come around and read them. All right. All right, I'm going to go. I'm going to start on this side of the room. You guys, you have it? I could make you guys read it, but I'll read it. It'll make it go faster. Have a complete plan. Do the math, make the part. Try not to screw up. Start with the design, create toolpaths, speeds and feeds, execute process. I like that. Give me a drawing and find a material, inspect, and clean up. Yeah, I'll do yours. Computer-controlled manufacturing science, building prototypes. The one that's circled? Yeah. Turn art into part through CNC machining. Clean up your damn mess. We have a winner so far. They have set the bar high. You ready? All right. Some inspiration, CNC machine make stuff. Clean up when you're done. Almost as good as theirs.
Almost, I'll take it.
Well, I like the clean up part. Anybody on this side didn't go yet? All right. Next side. Time we got 40. Perfect. Still have time. All right. What do we got? It first starts with art. Tool plan, good, go execute. Clean up your damn mess. I still like yours best.
I didn't write very neatly.
That's fine.
But I think
I don't read very neatly. Oh my God. She says she didn't write very neatly. This could be a font. Make art into part. Use math to not explode lab. Clean up your mess. All right. It's a contender. What do you got? Where is it? Oh, it's down here at the bottom? All right. Part was not held down. Was fixed down. Part was not fixed down. This is bad handwriting, by the way. Part was not fixed down. Part slammed right into the wall. Need to change my pants. We may have another winner. There's definitely contenders now.
I'm warning you, my handwriting is also bad. So you might not be able to read it.
It's not that bad.
You made a fun one and then you made it bad.
Yours is more like Sans comic, but Comic Sans, yeah, whatever. How do I make this? Use material and cam. Turn and finalize.
Oh, you didn't
I
like
read
the
it.
first one?
Wasn't that the one?
The first one on top, the blue.
Oh, I read the wrong one. Sorry.
No, that one's you read the actual one.
Oh, C term has started. My brain has yet to turn on. What was the topic? Who's next? Who's next? Did you guys go?
Yeah.
Yeah. Implement a plan. Use dimensions for detail. Turning, not lathing. These people that think they have bad handwriting and tell me, and then
Yeah.
setup and fixture. CAM software makes our toolpath. Inspect it, clean up.
They're the same one, just neater.
Yeah. Idea on a napkin. Haphazardly into CAM. Now I have my part. So did anybody besides me use an AI to write theirs? Prototype perfection, new designs crafted with care, innovative dreams soar. So have any of you guys tried any of these AIs to write stuff? I don't know. So I didn't tell you this, but haikus are supposed to be written in Japanese, and they're supposed to be about nature. They're supposed to be about like butterflies and flowers and stuff. So we're taking a lot of poetic license just by using English-ish, and so this bothered me at the beginning because I am kind of OCD about some things. So I Googled it because that's the answer to everything, and it turns out literature scholars have thought of this problem too. And they said, if you're writing haikus in English, 7, 6 syllables, it's okay. It's poetry. You can fudge the lines a little bit. But I do try to be a purist. Okay, so last on the agenda today was tomorrow. You can't see it. There it is. Last on the agenda today was tomorrow. So tomorrow we're going to be in Olin Hall, in the big lecture hall in Olin, unless there's another class there and we have to arm wrestle them. There was that confusion in Workday. The registrar's webpage always said that we were in this room on Wednesdays and in Olin on Mondays and Thursdays. That's what I put on my schedule, and that's what I put on the syllabus. Therefore, it must be correct. So I told IT to fix Workday. I did not consult with the registrar, so we could be screwed tomorrow. I checked. Yeah. If it is the case that the other class is in there, I looked through the window yesterday at the people that were in there. I think we could take them. Right. So I think we're good. I think that class meets on Mondays, Wednesdays, and Fridays, and that's why we don't get that room on Wednesday. We get to come over here. And so I mentioned I hate this room. I hate this room for the reasons I talked about at the beginning. But it's because I never really developed a method for using this room well. I mean, my 20-some years experience teaching has been more lecture style and more I'm the performer and you're the audience. But I decided not to complain about the Wednesdays being in here when I realized they were, even though I told them never, ever again put me in that room. Apparently, I don't have as much swing around here as I thought I did. And so what I'm going to try to do, and it screws, this is the reason the syllabus isn't posted yet. It screws up my entire lecture schedule. I'm going to try to have the Wednesdays be interactive activities and use this room the way it was designed to be used instead of like a lecture hall, which means I'm shifting stuff around on the schedule now to make sure, because I've never done this lecture first, for example. We usually talk about what is manufacturing because it's like a manufacturing class, and I have the habit of starting that way. So, by the way, that's what we'll talk about tomorrow. We're going to talk about manufacturing, why we should study it, why it's important. We're going to talk about the class and manufacturing engineering. We'll talk about the syllabus. Promise to have that done. You know, this is a lab class, right? You know, this is a lab class? Good. Because you have 4 hours a week of lab in this class. So you should know it's a lab class. There's a bookstore. There's a lab kit that you need to buy. It contains all the materials for the stuff we're going to make in the lab. So you do actually need to get that. We let you start the lab without it. So if you come to the first lab and you don't have your kit, we don't send you away. But if you come to the second lab and you don't have your kit, it's problematic for us. But we do have, so if something comes up and you forget to go to the bookstore and you're running late on the day that you have your first lab, don't freak out. We can work it out. Also, we have more students in each lab section than we have machine tools that we're going to use in each lab section. Therefore, you just don't have, you could go not first and go get your thing. You still have time. You had a question? It's the ME1800 lab kit. It's required. If you go to the bookstore, just tell them you need the ME1800 thing. It's a box, weighs about, I don't know, 5-6 pounds, maybe not that much. Feels heavy though. It's got mass. So you will feel that your $70 is well spent. Hey, there's no $250 book for the class. So, so the other thing about labs, no labs this week. You guys all got this, right? No labs this week. Is there no school on Monday? Is that true? There's no classes Monday, right? No classes Monday. So because there's no classes Monday, there will also be no lab on Tuesday next week. If you have lab scheduled on Tuesday next week, yeah, go ahead. Hold on, don't leave yet. I'm not done talking.
Are we required to get these safety glasses, or can we use ones that we have?
You should get your own safety glasses, but we do have visitor glasses if you need them.
Oh, I meant like the bookstore shows glasses for surgeons. I was asking.
Yeah, I mean, you're better off with your own glasses, but you can use ours. All right, one last thing. So no lab on Tuesday either. Labs are going to start on Wednesday. I know 75% of you right now are saying, but I don't have lab scheduled on Wednesday. That is correct. You will start lab on Thursday, not Wednesday. There are 4 sections in the class. One of them meets labs on Mondays and Wednesdays. The other 3 meet on Tuesdays and Thursdays. So we will start on Wednesday, but if you have Tuesday and Thursday lab, don't come on Wednesday because it's not your day. Okay? Oh, and all right, so you'll have a before your first lab assignment to do before the first lab. It'll go through all this stuff, but I just want to talk about it a little bit. When you get in the lab, wear shoes that cover your feet. No flip-flops, no Crocs. Wear shoes that cover your feet. It's better if they're leather. We don't make you wear safety shoes. Short sleeves, shorts are okay. If you have loose-fitting clothing, you should take it off, hang it on a hook, leave it over a chair or something like that. If you have, who's got one of these things? So I used to always, I don't know, for some reason I would walk around with mine hanging out of the pocket like this all the time, right? If you have one of these, stick it in your pocket. If you have jewelry around your neck, stick it inside or take it off, right? Any dangly stuff. We should wear tight-fitting clothes. And, oh yeah, hoodies. All you people with your hoodies. When's the last time you tied that, made a little bonnet out of it, right? Get rid of the strings or tuck them inside, okay? And if you have long hair, you want to tie it up or shave it off. I don't care which. I don't care which. And that's today's class.